Hello and welcome to Science After Dark. Before we begin tonight's journey, take a moment to gently tap the like button, and if you enjoy calm explorations of the universe like this one, consider subscribing to the channel so you never miss a new episode. And as always, I'd love to know where in the world you're watching or listening from tonight. Whether you're under the quiet glow of city lights, somewhere deep in the countryside beneath a sky full of stars, or perhaps listening while winding down for the night on the other side of the planet, let me know in the comments. Because wherever you happen to be right now, every single place on Earth shares something extraordinary. All of us, every continent, every ocean, every mountain and city, all exist inside the same vast cosmic story. And tonight, we're going to explore one of the biggest questions in that story. Did the Big Bang actually happen? It's a phrase that most of us have heard countless times. The moment when, according to modern cosmology, the universe began expanding from an incredibly hot and dense state nearly 13.8 billion years ago. But the phrase Big Bang can be misleading. It wasn't really an explosion. There wasn't a central point in space where everything suddenly burst outward like fireworks in the night sky. And perhaps most intriguingly of all, scientists didn't arrive at this idea by imagining the beginning of time. They arrived at it by looking carefully at the universe we see today. By measuring the faint glow of ancient radiation still drifting through space, by observing galaxies slowly moving away from one another across unimaginable distances, by studying the subtle patterns written across the largest structures in the cosmos. Piece by piece, observation by observation, a picture began to emerge, a picture suggesting that the universe was once smaller, hotter, and far denser than it is today. But science is never satisfied with a simple answer. Because if the universe really did begin in such an extreme state, it raises even deeper questions. What happened in the very first moments after cosmic expansion began? Did time itself start at that moment, or did something exist before it? Could the Big Bang have been only one phase in a much larger cosmic cycle, and might our universe even be just one of many? Tonight, we're going to slowly and calmly follow the trail of evidence that led scientists to the Big Bang model, and then explore the deeper mysteries that still surround it. From the earliest discoveries that revealed the universe is expanding, to the faint afterglow of ancient radiation left behind from the early cosmos, to bold modern ideas about inflation, quantum cosmology, and even possible multiverses. So settle in, relax, and let your mind drift gently outward into the cosmos. Because the story of the universe is not only the story of distant galaxies and ancient light, in a quiet way, it's also the story of how we came to understand where everything began. For as long as human beings have looked up at the night sky, a quiet question has followed us. Where did all of this come from? The stars scattered across the darkness, the faint band of the Milky Way stretching from horizon to horizon, the distant galaxies that modern telescopes reveal by the billions. Somewhere behind all of that beauty lies a deeper mystery, a question about beginnings. Did the universe always exist, stretching infinitely backward through time, or did it begin at some moment in the distant past? And if it did begin, how could scientists possibly know? These are not merely philosophical puzzles, they are scientific questions that researchers around the world attempt to answer using observation, mathematics, and careful measurement of the cosmos itself. The idea that the universe might have had a beginning is now most commonly associated with a phrase that has become part of everyday language: the Big Bang. It is a term that sounds dramatic, almost cinematic. It conjures images of a colossal explosion, a cosmic detonation throwing matter outward into empty space. But that image, while vivid, is not actually what cosmologists mean. The Big Bang is not an explosion that happened somewhere in space. It is a scientific model describing how space itself has changed over time. According to modern cosmology, the universe began in a state that was extraordinarily hot, extremely dense, and incredibly compact. From that early state, space began to expand. As space expanded, matter and energy spread outward, temperatures dropped, and the complex cosmic structures we see today slowly emerged. In other words, the Big Bang is best understood as the beginning of cosmic expansion. And that distinction matters, because if the universe is expanding today, then at earlier times it must have been smaller, and if we continue tracing that expansion backward far enough, we arrive at a time when the universe was unimaginably dense and hot. The Big Bang model describes the evolution of the universe from that early state onward. But one of the most remarkable aspects of this idea is that it did not begin as a philosophical guess. It emerged from evidence. Astronomers did not wake up one morning and decide that the universe must have begun with a bang. Instead, they began noticing patterns in the sky that required explanation. Patterns written into the light arriving from distant galaxies. Patterns hidden within faint radiation that fills the entire cosmos. Patterns revealed by the enormous distribution of galaxies across space. Taken individually, each of these discoveries tells a small part of the story, but when scientists combine them, they form a coherent picture that strongly suggests the universe has been expanding and evolving for billions of years. Cosmology, the scientific study of the universe as a whole, relies heavily on this approach. Rather than relying on speculation alone, cosmologists search for measurable clues left behind by cosmic history. The light from distant galaxies carries information about motion, temperature, and composition. Ancient radiation drifting through space carries information about the universe when it was only a few 100,000 years old. Even the large-scale arrangement of galaxies across billions of light-years carries subtle imprints of processes that happened long ago. By examining these clues, scientists can reconstruct the past in much the same way that geologists reconstruct the history of Earth from layers of rock. The difference is that the rocks in this case are made of light. Consider for a moment the scale of what astronomers are studying. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains anywhere from tens of millions to hundreds of billions of stars. Many of those stars are orbited by planets. The distances involved are so vast that even light, which travels at roughly 300,000 kilometers every second, takes millions or billions of years to cross them. That means when astronomers observe distant galaxies, they're not seeing them as they are today, they're seeing them as they were long ago. In this way, telescopes act as time machines. By looking deeper into space, scientists are effectively looking backward in time, observing earlier and earlier stages in cosmic history. And as those observations accumulated during the 20th century, something surprising became increasingly clear. The universe is not static, it is changing. Galaxies are moving away from one another. The universe itself appears to be expanding, gradually stretching the fabric of space across unimaginable distances. This discovery alone raised an intriguing possibility. If the universe is expanding now, then earlier in its history everything must have been closer together. Farther back still, matter would have been compressed into a smaller region, with higher temperatures and higher densities. Follow that logic all the way back and you arrive at a remarkable conclusion. The universe must once have been extremely hot and extremely dense. That idea forms the foundation of what scientists call the Big Bang model. But expansion alone is not enough to prove the theory. Science demands more than a single clue. Instead, cosmologists look for independent lines of evidence that all point in the same direction. And over time, several powerful pieces of evidence began to emerge. One of them comes from the motion of galaxies. Another comes from a faint glow of radiation that fills all of space. A third comes from the distribution of matter across enormous cosmic structures. Each of these discoveries tells us something different about the universe, and remarkably, all of them support the same broad conclusion. The universe has been expanding and evolving for billions of years. The story of how scientists uncovered these clues is one of the most fascinating intellectual adventures in human history. It involves astronomers peering through telescopes atop remote mountains, physicists developing equations to describe the behavior of space and time, engineers launching satellites that measure faint signals from the earliest epochs of cosmic history. Institutions such as the National Aeronautics and Space Administration, the European Space Agency, and research observatories around the world have all played important roles in building this understanding. Yet despite the enormous scale of the universe and the complexity of the physics involved, the core logic remains surprisingly simple. Look carefully at the universe, measure what you see, follow the evidence wherever it leads. Along the way, scientists sometimes discover that the universe behaves in ways that challenge our intuition. Concepts such as expanding space, cosmic background radiation, and quantum fluctuations in the early universe are not ideas that arise naturally from everyday experience. But once understood, they reveal a cosmos that is both elegant and deeply interconnected. The Big Bang model represents the current best attempt to describe that cosmic history. It explains how the universe expanded from an early hot state. It describes how matter formed the first atoms, how galaxies emerged, and how the large-scale structures we observe today slowly developed over billions of years. At the same time, it leaves many questions unanswered. What happened before the earliest moments we can describe with physics? Did time itself begin with cosmic expansion? Or does something deeper lie beneath our current understanding? Could the universe have undergone earlier cycles of expansion and contraction? And might our universe even be one among many? These are questions scientists are still exploring. For now, what we can do is follow the trail of evidence, because the universe, vast and ancient though it may be, has left behind clues written in starlight, clues carried by faint radiation drifting through the darkness, clues embedded in the enormous cosmic structures stretching across the observable universe. By examining those clues carefully, humanity has begun to reconstruct a story that stretches back nearly 14 billion years. A story about how the universe evolved from an early hot and dense state into the immense cosmic landscape we inhabit today. And as we begin tracing that story, the first step is understanding one of the most surprising discoveries in the history of astronomy. The moment when scientists realize that the universe itself is expanding. For much of human history, the universe was imagined as something timeless, a vast stage that had always existed, stretching endlessly in every direction, unchanging and eternal. Stars rose and set, constellations slowly shifted over centuries, planets wandered through the sky in complex patterns, but the larger cosmic structure appeared stable, almost permanent. To observers on Earth, the heavens seemed like an enormous clockwork system that had simply always been there. Even as astronomy advanced during the 18th and 19th centuries, this assumption remained largely intact. Telescopes revealed new wonders. Astronomers discovered nebulae, star clusters, and distant galaxies. But the prevailing belief among scientists was that the universe itself was fundamentally static. It was not growing or shrinking. It was simply there. This idea was so deeply embedded in scientific thinking that even one of the greatest physicists in history initially assumed it must be true. That physicist was Albert Einstein. In 1915, Einstein introduced a revolutionary theory that transformed the scientific understanding of gravity. The theory was called general relativity. Before Einstein, gravity had been described using the work of Isaac Newton. Newton's theory imagined gravity as a force that pulled objects toward one another across space. The Earth pulled the Moon, the Sun pulled the planets, and every object with mass exerted a gravitational attraction on every other object. Einstein proposed something far more subtle and elegant. According to general relativity, gravity is not simply a force acting across empty space. Instead, gravity arises because mass and energy bend the fabric of spacetime itself. Spacetime is the four-dimensional structure that combines the three dimensions of space with the dimension of time. Massive objects such as stars and galaxies distort this structure, creating curvature. Objects moving through that curved spacetime follow paths that appear to us as gravitational motion. A helpful analogy often used by physicists involves imagining a stretched rubber sheet. If a heavy ball is placed on the sheet, the surface dips downward. Smaller balls rolling nearby naturally follow curved paths toward the heavy object. In reality, spacetime is not a sheet, and it does not bend downward into anything, but the analogy helps illustrate how mass can influence the geometry of the universe. Einstein's equations of general relativity describe exactly how mass and energy shape spacetime. One simplified way of expressing the relationship captured by those equations is the statement often summarized as, "Spacetime tells matter how to move, and matter tells spacetime how to curve." It is an elegant partnership between geometry and physics. Yet when Einstein applied his new equations to the universe as a whole, something unexpected happened. The mathematics suggested that a universe filled with matter could not remain perfectly static. Gravity would cause matter to pull together over time. In other words, the universe should begin collapsing inward under its own gravitational attraction. This conclusion deeply troubled Einstein. At the time, there was no observational evidence suggesting that the universe was changing. Most astronomers still assumed the cosmos was stable and eternal. So Einstein made a bold decision. He modified his equations. To counteract the gravitational pull of matter, he introduced a new term into the equations of general relativity. This term became known as the cosmological constant. The cosmological constant represents a kind of repulsive effect built into spacetime itself. Its purpose in Einstein's original model was simple. It pushed outward just enough to balance the inward pull of gravity. The result was a delicate cosmic equilibrium. Gravity pulled matter together, while the cosmological constant pushed space apart. If perfectly balanced, the universe could remain static and unchanging, at least mathematically. For a time, this seemed like a satisfactory solution. Einstein had preserved the assumption of a stable universe, while keeping his theory of general relativity intact. But the story did not end there. Across Europe, other physicists began exploring the implications of Einstein's equations more freely. One of the most important among them was a Russian mathematician and physicist named Alexander Friedmann. In the early 1920s, Friedmann carefully examined Einstein's equations without insisting that the universe must remain static. Instead, he allowed the mathematics to speak for itself. What he discovered was remarkable. The equations naturally produce solutions in which the universe expands or contracts over time. In these models, the distance between galaxies would gradually increase as space itself stretches. Alternatively, the universe could shrink if gravity dominated. Friedmann showed that a dynamic universe was not just possible within general relativity. It was actually one of the most natural outcomes of the equations. In fact, a perfectly static universe turned out to be an unstable mathematical balancing act. Even a tiny disturbance would cause the universe to begin expanding or collapsing. Initially, Einstein resisted Friedmann's conclusions. At first, he believed Friedmann had made a mathematical mistake, but after reviewing the calculations more carefully, Einstein acknowledged that the solutions were correct. The mathematics of general relativity allowed a universe that evolves over time. This realization was quietly revolutionary. At the time, however, it remained largely theoretical. There was still no clear observational evidence that the universe was expanding or changing. Friedmann had shown what the equations allowed, but the sky itself had not yet confirmed it. Nevertheless, an important shift had begun. For the first time, physicists were seriously considering the possibility that the universe might not be eternal and unchanging after all. Instead, the cosmos might have a history, a beginning, perhaps, or at least a past that looked very different from the present. These early theoretical ideas planted the seeds for a new kind of cosmology, one in which the universe evolves, one in which the large-scale structure of space itself changes over time. And although Friedmann's work remained relatively obscure during his lifetime, the implications of his calculations would soon become impossible to ignore. Because within a few years, astronomers studying distant galaxies would make a discovery that seemed almost unbelievable. The universe itself appeared to be expanding. In the early decades of the 20th century, astronomy was undergoing a quiet revolution. For centuries, the night sky had appeared stable. Stars seemed fixed in place, and the few wandering planets followed predictable paths. Even when astronomers began observing faint spiral nebulae through powerful telescopes, there was still uncertainty about what those objects truly were. Some scientists believed these spirals were clouds of gas within our own galaxy, the Milky Way. Others suspected they might be distant stellar systems far beyond our own. The question was not trivial. If those spirals were truly separate galaxies, then the universe would be far larger than anyone had imagined. One of the astronomers determined to solve this mystery was Edwin Hubble. Hubble worked at the Mount Wilson Observatory in California, high in the San Gabriel Mountains above the city of Los Angeles. At that time, Mount Wilson housed one of the most powerful astronomical instruments ever built. The Hooker telescope, with a mirror 100 inches in diameter, allowed astronomers to see deeper into space than any telescope before it. Using this instrument during the 1920s, Hubble began carefully observing spiral nebulae. His work focused on identifying a particular type of star known as a Cepheid variable. Cepheid variable stars are extremely useful for astronomy because their brightness changes in a regular and predictable pattern. The relationship between the period of that brightness variation and the star's intrinsic luminosity had been discovered earlier by the astronomer Henrietta Swan Leavitt at the Harvard College Observatory. Leavitt's work revealed that if astronomers measure the time it takes for a Cepheid star to brighten and dim, they can determine how luminous the star truly is. Once the true brightness is known, comparing it with the brightness seen from Earth allows astronomers to calculate the star's distance, It is a bit like seeing a distant lighthouse. If you know how bright the lighthouse truly is, then the faintness of the light tells you how far away it must be. Hubble identified Cepheid variables inside several spiral nebulae. When he calculated their distances, the results were astonishing. These objects were far beyond the boundaries of the Milky Way galaxy. What had once been called nebulae were actually entire galaxies of their own, each containing billions of stars. The universe had suddenly become vastly larger. But Hubble's discoveries did not stop there. Astronomers had already begun studying the light from distant galaxies using a technique called spectroscopy. Spectroscopy involves splitting light into its component wavelengths, much like a prism creating a rainbow from sunlight. Each chemical element produces distinctive patterns of light known as spectral lines. These spectral lines serve as fingerprints, allowing scientists to identify the composition of stars and galaxies. But spectral lines reveal something else as well. They can shift. If a light source moves toward an observer, its wavelengths become slightly shorter. This effect is known as blue shift. If the source moves away, the wavelengths stretch and become longer. This effect is called redshift. The phenomenon is a version of the Doppler effect, which many people have experienced when hearing the changing pitch of a passing ambulance siren. As the vehicle approaches, the sound waves compress and the pitch rises. As it moves away, the waves stretch and the pitch lowers. Light behaves in a similar way. When astronomers examined the spectra of distant galaxies, they noticed something remarkable. Most galaxies exhibited redshift. Their spectral lines were shifted toward longer wavelengths, indicating that the galaxies were moving away from Earth. This observation had been noticed earlier by astronomer Vesto Slipher at the Lowell Observatory in Arizona, who had measured the radial velocities of several spiral nebulae. But Hubble took the investigation further. He combined Slipher's redshift measurements with his own distance measurements of galaxies. The result revealed a striking pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship became known as Hubble's law. It can be expressed in words quite simply. The recessional velocity of a galaxy equals the Hubble constant multiplied by the distance to that galaxy. In other words, the speed at which galaxies recede from us increases in direct proportion to their distance. Galaxies twice as far away move away roughly twice as fast. Galaxies 10 times farther away move away roughly 10 times faster. The pattern was not subtle. It appeared clearly in the observational data. And its implications were extraordinary. The galaxies were not merely drifting randomly through space. Space itself seemed to be expanding. To understand this idea, it helps to imagine a simple analogy often used by cosmologists. Picture a loaf of raisin bread dough rising in an oven. As the dough expands, the raisins embedded within it move farther apart from one another. Each raisin sees all the others drifting away. Importantly, there is no single raisin at the center of the expansion. The expansion happens everywhere within the dough simultaneously. The same concept applies to the expanding universe. Galaxies are like raisins embedded within the fabric of space. As space expands, the distance between galaxies increases. From the perspective of any given galaxy, it appears as though all other galaxies are moving away. This means that our location in the universe is not special. Observers in another galaxy billions of light years away would see the same pattern. From their perspective, our Milky Way would appear to be receding from them as well. The expansion of the universe occurs everywhere at once. There is no central explosion point and no outer edge where galaxies are flying into empty space. Instead, the fabric of space itself is stretching. This realization fundamentally changed humanity's understanding of the cosmos. If the universe is expanding today, then it must have been smaller in the past. That conclusion follows directly from the mathematics of expansion. Imagine watching a movie of the universe in reverse. Galaxies would gradually move closer together. Distances between clusters would shrink. The cosmic structures we see today would compress. Travel far enough backward in time, and the universe would become extremely dense and extremely hot. In that early state, matter and energy would be packed tightly together. The discovery of cosmic expansion therefore suggested something profound. The universe has a history. It is not static or eternal in the way scientists once assumed. Instead, it has been evolving over billions of years. This insight provided one of the first major pieces of evidence supporting what would later become known as the Big Bang model. The universe appears to be expanding from an earlier state that was smaller, hotter, and denser than the one we observe today. Of course, the discovery of expansion did not immediately answer every question. Scientists still needed to understand what conditions were like in that early universe. They needed to search for additional evidence that could confirm or challenge the emerging picture. But one thing was now clear. The cosmos was not a static stage. It was dynamic. It was changing. And the light arriving from distant galaxies was quietly revealing a universe that had been growing and evolving for billions of years. Not long after astronomers began realizing that galaxies were scattered far beyond the Milky Way, another idea quietly emerged. It did not begin in an observatory dome or a crowded laboratory, but in the careful mathematical work of a man who occupied a rather unusual position in the scientific world. His name was Georges Lemaitre. Lemaitre was a Belgian physicist, astronomer, and also a Catholic priest. That combination might sound surprising today, but in the early 20th century it was not entirely unheard of for scholars to move comfortably between theology and science. For Lemaitre, the two fields occupied different domains. His religious beliefs addressed philosophical questions, while physics and astronomy described the measurable workings of the universe. What made Lemaitre particularly remarkable was his ability to connect ideas from several emerging fields of science. He understood Albert Einstein's theory of general relativity. He followed the latest astronomical observations of distant galaxies, and he was willing to explore conclusions that other scientists were hesitant to accept. In the late 1920s, Lemaitre began examining the implications of cosmic expansion more deeply. If galaxies were moving away from one another, as Edwin Hubble's observation suggested, then the universe must have been smaller in the past. That much seemed unavoidable. But Lemaitre pushed the idea further. He imagined what would happen if one continued tracing the expansion backward in time, step by step, across billions of years. Galaxies would move closer together, clusters of galaxies would merge. The density of matter throughout the universe would steadily increase. Temperatures would rise as particles were compressed into smaller regions of space. Eventually, the entire observable universe would converge into an extremely compact state. In 1931, Lemaitre proposed a bold interpretation of this idea. He suggested that the universe might have originated from what he called a primeval atom. The phrase was meant to describe an initial state in which all matter and energy in the universe were concentrated into an incredibly dense and extremely hot region. This was not yet the Big Bang theory as it is understood today, but it was a remarkable early step toward that concept. Lemaitre envisioned the beginning of cosmic history as a kind of explosive expansion from this primeval state. He sometimes referred to the event as the beginning of space and time themselves. In other words, rather than imagining matter exploding into pre-existing empty space, Lemaitre proposed that space itself expanded outward from an initial condition of extreme density. It was a radical suggestion. And like many radical scientific ideas, it was met with skepticism. Part of the hesitation came from philosophical concerns. Many scientists at the time were uncomfortable with the notion of a universe that had a beginning. The idea sounded too similar to religious creation stories, and some researchers worried that it might blur the boundary between science and theology. Ironically, Lemaitre himself was careful to keep those boundaries separate. He insisted that his scientific model did not attempt to explain why the universe existed, only how it evolved from an early physical state. Another reason for skepticism was the lack of supporting evidence. Astronomers had observed galaxies moving away from one another, but the details of the early universe were still largely unknown. There were no measurements yet of cosmic background radiation. The chemistry of the early cosmos had not been studied in detail. Much of the theoretical framework still needed to be developed. Even Albert Einstein initially resisted Lemaitre's interpretation. When the two men met in the early 1930s, Einstein reportedly told Lemaitre that, while his calculations were correct, the physical interpretation was, in Einstein's words, abominable. It was not meant as an insult to Lemaitre personally. Rather, Einstein found the idea of a cosmic beginning difficult to accept. Yet the mathematics underlying Lemaitre's work remained sound. His reasoning followed directly from the principles of general relativity combined with observational evidence for cosmic expansion. If space is expanding today, then earlier in time the universe must have been denser and hotter. That conclusion became increasingly difficult to avoid. Over time, Lemaitre's ideas began to influence other researchers. Physicists started exploring what conditions might have been like in the early universe. If matter were compressed into such a dense state, temperatures would have been extraordinarily high. At sufficiently high temperatures, atoms could not exist. Even atomic nuclei would struggle to remain stable. Instead, the universe would have consisted of an intensely energetic mixture of particles and radiation. This picture hinted at a universe that evolved through different stages. First, an extremely hot and dense beginning, then gradual cooling as space expanded, eventually the formation of atomic nuclei, atoms, stars, and galaxies. In many ways, Lemaitre had provided the conceptual foundation for what would later become known as Big Bang cosmology. His primeval atom idea suggested that cosmic history might be traced backward toward a specific physical state in the distant past. Importantly, Lemaitre did not claim to understand every detail of that beginning. He simply recognized that the expanding universe implied a dramatically different past, and that past might have been characterized by extreme density and intense heat. One could imagine the universe at that early stage as something like an unimaginably compressed cosmic furnace. Temperatures would have been so high that matter existed in forms very different from anything we encounter in the present day. In the earliest moments, the universe may have been filled with elementary particles and radiation interacting constantly within a searing environment. As expansion continued, that fiery plasma would gradually cool. New structures would become possible. Protons and neutrons would combine into atomic nuclei. Electrons would eventually bind to those nuclei to form atoms. Over hundreds of millions of years, gravity would gather matter into the first stars and galaxies. In this sense, the idea of a hot early universe provided a powerful framework for understanding cosmic evolution. The universe was not simply expanding, it was also cooling, changing, and becoming more structured over time. Although Lemaitre's proposal initially remained controversial, history would eventually recognize it as one of the most important insights in modern cosmology. His willingness to combine theoretical physics with astronomical observation opened a new path for understanding the universe. And as scientists continued searching for evidence, they would soon discover clues that strongly supported the idea of a hot and dense beginning. Clues written not only in the motion of galaxies, but also in faint radiation that had been quietly travelling through the universe for billions of years. As the idea of a universe that changes over time began to take shape, scientists found themselves facing a deeper question. If the universe is expanding today, what does that really mean for its overall history? One possibility was the emerging idea that the cosmos began from an extremely hot and dense state in the distant past. This concept, inspired by the work of Georges Lemaitre, suggested that the universe had a kind of beginning. But not everyone was comfortable with that conclusion. In fact, during the middle of the 20th century, a very different cosmological model gained significant attention. This alternative was known as the steady-state theory. The steady-state model was developed primarily by three physicists working in Britain: Fred Hoyle, Hermann Bondet, and Thomas Gold. Each of them brought a slightly different perspective, but together they built a cosmological picture that challenged the idea of a universe with a beginning. Their proposal was both elegant and bold. They accepted the observational evidence that galaxies appear to be moving away from one another. In other words, they agreed that the universe is expanding, but they rejected the idea that expansion implied a dramatic origin event in the distant past. Instead, they proposed that the universe has always existed in roughly the same overall state. According to the steady-state theory, the universe expands continuously, but its large-scale appearance never truly changes. Galaxies move farther apart as space stretches. However, new matter is continuously created to fill the gaps left by that expansion. This ongoing creation of matter ensures that the average density of the universe remains constant over time. The key principle behind this idea was called the perfect cosmological principle. The perfect cosmological principle extends an earlier concept known as the cosmological principle. The original cosmological principle states that, on large scales, the universe looks the same in every direction and from every location. The perfect cosmological principle adds an additional requirement. It states that the universe must also look the same at all times, not just similar across space, but unchanging across time. In other words, the universe would be eternal and statistically identical throughout its history. If you could somehow observe the cosmos billions of years in the past or billions of years in the future, its overall appearance would remain essentially the same. Galaxies would form and evolve locally, but the universe as a whole would maintain a steady average density and structure. To make this idea work, Hoyle, Bondi and Gold proposed that matter must be continuously created throughout space. This creation process would occur at an incredibly slow rate. In fact, the amount of new matter required is surprisingly tiny. Calculations suggested that only about one hydrogen atom would need to appear in each cubic meter of space, roughly every billion years, in order to maintain a constant density as the universe expands. That rate is so small that it would be almost impossible to detect directly. From a practical standpoint, the steady-state universe would look very similar to the expanding universe described by Lemaitre's earlier ideas, at least when observing relatively nearby galaxies. But there was a crucial philosophical difference. In the steady-state model, the universe has no beginning and no end. It simply exists, forever expanding, yet always maintaining the same overall character. For some scientists, this idea felt far more comfortable. The concept of a universe with a beginning raised difficult questions. What caused that beginning? What existed before it? Did time itself start at that moment? Those questions ventured into territory that physics had not yet learned how to describe. An eternal universe avoided those complications. It also resonated with the long tradition in science of preferring models that do not require special starting conditions. Fred Hoyle, in particular, became one of the most prominent defenders of the steady-state theory. Hoyle was a brilliant astrophysicist who made major contributions to understanding how stars create heavy chemical elements. His work on stellar nucleosynthesis helped explain how elements such as carbon, oxygen, and iron are forged inside stars. Yet when it came to cosmology, Hoyle strongly opposed the idea of a cosmic beginning. In fact, the famous phrase Big Bang originally emerged during a radio broadcast in the late 1940s when Hoyle was discussing cosmological models for a general audience. While describing the rival theory that the universe began in a sudden explosive expansion, he referred to it somewhat dismissively as the Big Bang. The name stuck. Ironically, the phrase that Hoyle used to criticize the idea eventually became the widely accepted term for the model he opposed. During the 1950s and early 1960s, both the steady-state theory and the emerging Big Bang model remained active contenders. Astronomers and physicists debated their merits in journals, conferences, and university lecture halls. Each theory attempted to explain the same observations. Both accepted that galaxies were moving apart. Both used general relativity to describe the large-scale behavior of the universe. The difference lay in how they interpreted cosmic history. One model described a universe that evolves from an extremely hot and dense past. The other described a universe that expands forever while remaining statistically unchanged. This competition between ideas turned out to be incredibly valuable for science. When multiple theories attempt to explain the same phenomenon, researchers must look for observations that can distinguish between them. In other words, the debate encouraged scientists to search for new evidence. Astronomers began asking deeper questions about the structure of the universe. Does the number of galaxies change when we look farther into space and therefore farther into the past? Do distant galaxies appear different from nearby ones? Is there any lingering radiation left over from a hot early stage of cosmic history? The search for answers to questions like these would eventually provide crucial tests for both models. And as new observations accumulated, the universe itself would begin revealing which of these competing visions most closely matched reality. In the end, the debate between the steady-state theory and the Big Bang model played a crucial role in shaping modern cosmology. It forced scientists to examine their assumptions carefully, to design new experiments, and to look more deeply into the history written across the cosmos. Sometimes the most important scientific progress does not come from immediate agreement. It comes from thoughtful disagreement, from the willingness to ask difficult questions and follow the evidence wherever it leads. And in this case, the evidence was quietly waiting in the faintest signals drifting through the universe. As astronomers and physicists continued to debate the large-scale history of the universe, an important question began to emerge. If the universe really did begin in a state that was extremely hot and dense, then that early phase should have left behind observable traces. In science, theories gain strength when they make predictions that can be tested. A powerful theory does more than explain known facts. It suggests new phenomena that researchers can look for. During the late 1940s, a small group of physicists began exploring what the early universe might have looked like if it had once been far hotter than it is today. One of the leading figures in this effort was George Gamow. Gamma was a Russian-born physicist who later worked in the United States. He had already made important contributions to nuclear physics, particularly in understanding how atomic nuclei behave under extreme conditions. Gamma had a playful personality and a fondness for creative thinking, but beneath the humour lay a serious scientific curiosity about the earliest moments of cosmic history. Working alongside Gamma were two collaborators, Ralph Alpher and Robert Herman. Together they began asking a fundamental question. If the universe began in an extremely hot and dense state, what would that environment actually have been like? To answer this, they turned to the laws of thermodynamics and nuclear physics. At very high temperatures, matter behaves very differently from the way it does in the cooler universe we experience today. Under ordinary conditions, atoms consist of nuclei surrounded by electrons. But when temperatures climb high enough, atoms cannot remain intact. Electrons are stripped away from nuclei, forming an energetic mixture known as plasma. If the temperature increases even further, atomic nuclei themselves can begin interacting in complex nuclear reactions. Gamow and his colleagues realized that if the early universe had been extremely hot, it would have been filled with a dense plasma of particles and radiation. Photons, which are particles of light, would have been constantly interacting with electrons and atomic nuclei. The entire cosmos would have resembled an enormous glowing furnace, with radiation bouncing in every direction. In such an environment, light would not travel freely. Photons would scatter repeatedly as they collided with charged particles. The universe would have been opaque, somewhat like the interior of a star. However, the universe was also expanding. As space expanded, the density of matter would gradually decrease, and the temperature would slowly drop. Over time, the conditions would change enough that electrons could combine with atomic nuclei to form stable atoms. Once that happened, photons would no longer scatter as frequently. Instead, light could finally travel long distances without being constantly absorbed and re-emitted. At that moment, the universe would become transparent. Games, Alpha, and Herman realized something remarkable about this transition. When the universe first became transparent, an enormous amount of radiation would suddenly be released to travel freely through space, and that radiation should still exist today. It would be the ancient light from the early universe itself, preserved as a faint glow spread throughout all of space. Of course, the universe has been expanding for billions of years since that time. As space stretches, the wavelengths of light travelling through it stretch as well. This process is closely related to the same phenomenon responsible for the redshift observed in distant galaxies. When wavelengths stretch, their energy decreases and their temperature drops. Gamow and his collaborators calculated that radiation produced in the early hot universe would gradually cool as the universe expanded. By the time it reached the present era, that radiation would no longer appear as visible light. Instead, it would exist as extremely faint microwave radiation. Microwaves occupy a region of the electromagnetic spectrum with wavelengths longer than visible light but shorter than radio waves. Today, we often associate microwaves with kitchen appliances, but they are simply another form of electromagnetic radiation, governed by the same physical laws as visible light and radio signals. Gamow, Alpha, and Herman estimated that the temperature of this leftover radiation should now be only a few degrees above absolute zero. Absolute zero represents the coldest possible temperature, where particles possess the minimum amount of thermal energy allowed by physics. On the Kelvin temperature scale used in scientific research, absolute zero corresponds to 0 Kelvin. Gamow's team predicted that the leftover radiation from the early universe might have a temperature of only a few degrees Kelvin. Even more importantly, they predicted that this radiation should be present everywhere in the sky. Because the early universe was extremely dense and nearly uniform, the radiation released when it became transparent should appear almost identical in every direction. No matter where astronomers pointed their instruments, they should detect the same faint background glow. The entire universe would be filled with this relic radiation. In modern terminology, this predicted signal would later be called the cosmic microwave background. But at the time, the idea remained largely theoretical. Detecting such faint radiation would require sensitive instruments, and the technology of the 1940s and 1950s was not yet well suited for the task. For several years, the prediction remained quietly recorded in scientific papers without attracting widespread attention. Meanwhile, astronomers continued observing galaxies and refining measurements of cosmic expansion. The debate between the steady-state model and the evolving universe model continued. but the prediction of leftover radiation offered a potentially decisive test. If the universe had once been extremely hot, this radiation should still exist. If the universe had always existed in a steady state, then there would be no reason for such a background glow to fill the cosmos. In other words, the presence or absence of this faint radiation could help determine which picture of the universe was correct. Sometimes in science, predictions wait patiently for years before the right tools or circumstances appear. In this case, the discovery would come not from an experiment designed to test the theory, but from an entirely different investigation. And in a twist that scientists sometimes describe with a quiet smile, the evidence for the early universe would reveal itself almost by accident. In the mid-1960s, two radio astronomers working in New Jersey encountered a signal that would quietly transform our understanding of the universe. Their names were Arno Penzias and Robert Wilson. Both researchers were working at Bell Telephone Laboratories, often simply called Bell Labs, one of the most important research institutions in the United States during the 20th century. Bell Labs had contributed to developments ranging from telecommunications to the invention of the transistor. Among the equipment available, there was a large and unusual radio antenna known as the Holmdel Horn antenna. The antenna had originally been designed for satellite communication experiments, particularly to study signals bouncing between Earth and early communication satellites. Its shape resembled a large metal horn lying on its side, carefully engineered to minimize unwanted noise from the surrounding environment. For radio astronomy, this design turned out to be extremely useful. Penzias and Wilson began using the antenna to measure faint microwave signals coming from space. Their goal was to study radio emissions from the Milky Way and other astronomical sources. However, almost immediately they encountered a problem. No matter where they pointed the antenna, their instruments detected a faint background noise. It was not particularly strong, but it was persistent. The signal appeared to come from every direction in the sky. At first, the two astronomers assumed the noise must be caused by something local. Radio measurements are easily affected by interference from the environment, including electronic equipment, atmospheric effects, and even nearby cities. Penzias and Wilson began carefully investigating every possible source of contamination. They checked their receivers and electronic circuits. They recalibrated their instruments repeatedly. They considered whether signals from New York City, located several dozen kilometers away, might be interfering with the measurements. Still, the signal remained. The mysterious noise corresponded to radiation, with a temperature of about 3 degrees above absolute zero. On the Kelvin temperature scale used in physics, absolute zero represents the coldest possible temperature. A signal corresponding to only 3 Kelvin was extremely faint, but unmistakably present. More puzzling still, the signal appeared perfectly uniform. No matter where the antenna pointed in the sky, the background radiation remained almost exactly the same. At one point, the researchers even considered whether biological contamination might be responsible. The antenna had become home to a pair of pigeons, and the birds had left behind what the scientists politely referred to as white dielectric material. In less formal language, it was pigeon droppings. Penzias and Wilson carefully cleaned the antenna and removed the pigeons, hoping that the mysterious noise might disappear. But the signal stubbornly persisted. Eventually it became clear that the radiation was not coming from any local source. It appeared to be coming from the universe itself. At roughly the same time, a group of physicists at Princeton University had been working on a completely different problem. The Princeton group included Robert Dicke, Jim Peebles, Peter Roll, and David Wilkinson. These scientists were studying the theoretical prediction that a hot early universe should have left behind a faint background glow of radiation. Jim Peebles in particular had been calculating what properties such radiation might have today. The expected temperature was only a few degrees above absolute zero, and the radiation should be present uniformly across the entire sky. When Penzias and Wilson learned about the Princeton research, the connection quickly became clear. The mysterious microwave signal detected at Bell Labs matched the theoretical prediction almost perfectly. What they had found was the leftover radiation from the early universe. This radiation soon became known as the cosmic microwave background. The phrase describes exactly what it is. Cosmic because it fills the entire universe. Microwave because its wavelengths fall within the microwave region of the electromagnetic spectrum. Background because it appears as a faint glow present everywhere in space. The cosmic microwave background is essentially ancient light. It has been travelling through the universe for nearly 14 billion years. Its origin traces back to a time when the universe was only a few 100,000 years old, when matter and radiation were first able to move freely through space. Before that time, the universe had been filled with a dense plasma of charged particles and photons, constantly scattering off one another. Once the universe cooled enough for electrons to combine with atomic nuclei, light was finally able to travel long distances without interruption. The photons released during that transition are the very same photons that now form the cosmic microwave background. Over billions of years of cosmic expansion, their wavelengths stretched dramatically. What began as intense radiation from a hot early universe gradually cooled into the faint microwave glow detected by Penzias and Wilson. The discovery was announced in 1965 through two scientific papers published in the Astrophysical Journal. One paper, written by Penzias and Wilson, described the observational detection of the unexplained microwave signal. The other, written by the Princeton group, explained its cosmological interpretation. Together, the two papers provided one of the most important pieces of evidence in modern cosmology. The cosmic microwave background strongly supported the idea that the universe had once been extremely hot and dense. It was precisely the kind of relic radiation predicted by George Gamow, Ralph Alpher, and Robert Herman nearly 2 decades earlier. For the Big Bang model, the discovery was a powerful confirmation. For the steady-state theory, however, the situation was far more difficult. The steady-state model proposed that the universe had always existed in roughly the same overall condition. It did not include a hot early phase in which radiation filled the cosmos. As a result, the theory had no natural explanation for the presence of a universal background glow with a temperature of only a few degrees above absolute zero. Scientists attempted various modifications to the model, but none provided a convincing explanation for the observation. Gradually, the balance of evidence began shifting toward the evolving universe, picture first suggested by Lemaitre, and explored further by Gamow and his colleagues. In recognition of their discovery, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics in 1978. Their accidental measurement had revealed a signal that had been travelling through the universe since near the beginning of cosmic history. A faint whisper of ancient light, a relic from a time when the universe itself was young, and with that discovery, the idea that the universe once existed in a hot and dense state became far more than speculation. It had become an observable fact written across the sky itself. To understand why the cosmic microwave background is so important, it helps to imagine what the universe was like long before the first stars ever existed. In the earlier stages after cosmic expansion began, the universe was a place of extraordinary heat and density. Temperatures were so high that atoms could not exist. Instead, matter formed an energetic plasma consisting mainly of protons, electrons, and atomic nuclei moving rapidly through space. Photons, the particles of light, were everywhere as well. But in that environment, light did not travel freely. Photons constantly collided with charged particles, especially electrons. Each time a photon encountered an electron, it scattered in a different direction. This process is known as Thomson scattering, a well-understood interaction between electromagnetic radiation and charged particles. Because of this constant scattering, the early universe behaved somewhat like the interior of a star or the glowing gas inside a fluorescent lamp. Light was present everywhere, yet it could not move very far before encountering another particle. In effect, the universe was opaque. Trying to see through that plasma would have been like trying to look through dense fog illuminated by a bright lamp. The light is there, but it cannot travel in a straight line. However, the universe was expanding. As space expanded, the density of matter slowly decreased and temperatures gradually fell. Over hundreds of thousands of years, the cosmic plasma cooled enough for a major transition to occur. Electrons, which had previously been moving freely, began to combine with positively charged protons. When a negatively charged electron binds with a proton, the result is a neutral hydrogen atom. This transition is known in cosmology as recombination. The name might sound slightly misleading, since electrons and protons had never actually combined before in the history of the universe. But the term was borrowed from atomic physics, where it describes electrons recombining with ions in laboratory plasmas. In the cosmic context, recombination refers to the moment when the universe cooled enough for stable neutral atoms to form. This event dramatically changed how light behaved. Neutral atoms do not scatter photons nearly as efficiently as free electrons do. As a result, photons were suddenly able to travel enormous distances without constant interruption. For the first time in cosmic history, light could move freely through space. The universe had become transparent. This transition occurred when the universe was roughly 380,000 years old. Compared with the universe's current age of roughly 13.8 billion years, that moment arrived very early in cosmic history. The photons released during this transition began a journey that has continued ever since. They travelled outward across the expanding universe, spreading in every direction. And remarkably, many of those photons are still moving through space today. They are the photons detected as the cosmic microwave background. When these photons were first released, the universe was still extremely hot by modern standards. The radiation had a temperature of roughly 3000 Kelvin, comparable to the surface temperature of a warm star. But the universe continued to expand. As space stretches, the wavelengths of travelling photons stretch as well. This process is known as cosmological redshift. When a photon's wavelength becomes longer, its energy decreases. That decrease in energy corresponds to a lower temperature. Over billions of years of expansion, the radiation from the early universe gradually cooled. Today, the cosmic microwave background has a temperature of about 2.7 Kelvin. That is only 2.7 degrees above absolute zero. Absolute zero represents the theoretical temperature at which particles possess the minimum possible thermal motion allowed by the laws of physics. In everyday terms, 2.7 Kelvin is unimaginably cold. Yet the cosmic microwave background still fills every corner of space with this faint residual warmth. Although the radiation is extremely weak, its properties are astonishingly precise. One of the most important characteristics of this radiation is its spectrum. In physics, a spectrum describes how radiation is distributed across different wavelengths or frequencies. Certain physical processes produce distinctive spectral patterns. Radiation emitted by objects that are heated to a particular temperature follows a very specific pattern known as a blackbody spectrum. A blackbody is an idealized object that absorbs and emits radiation perfectly according to its temperature. The radiation from a blackbody obeys a precise mathematical distribution determined by the laws of thermodynamics and quantum mechanics. When scientists examined the cosmic microwave background in detail, they discovered something extraordinary. Its spectrum matched the exact pattern expected from blackbody radiation. Not approximately, almost perfectly. This remarkable result was confirmed in great detail by a satellite mission launched by the National Aeronautics and Space Administration, commonly known as NASA. The spacecraft was called the Cosmic Background Explorer, or COBE. COBE was launched in the late 1980s with the specific goal of studying the cosmic microwave background with far greater precision than had been possible using ground-based instruments. One of its instruments measured the spectrum of the background radiation with extraordinary accuracy. The results showed that the cosmic microwave background follows the blackbody radiation curve corresponding to a temperature of approximately 2.7 Kelvin. The match between theory and observation was so precise that it became one of the strongest confirmations of the hot early universe model. The reason this measurement matters is subtle but powerful. A blackbody spectrum indicates that the radiation once existed in a state of thermal equilibrium with matter. In other words, the photons and particles in the early universe must have interacted intensely within a hot environment before eventually separating and travelling freely. This is exactly what the Big Bang model predicts. The universe began in a hot and dense state where radiation and matter were tightly coupled. As expansion continued and temperatures dropped, recombination occurred and photons began their long journey through space. The cosmic microwave background therefore provides something extraordinary. It is a direct snapshot of the universe at the moment it first became transparent. When astronomers observe this radiation today, they are effectively looking back in time to when the universe was only 380,000 years old. Compared with the billions of years that followed, that moment lies astonishingly close to the beginning of cosmic history. The faint microwave glow filling the sky is not merely background noise, it is ancient light. Light that has been travelling across the universe for nearly 14 billion years. And within that ancient radiation lies an extraordinary amount of information about the early universe. Patterns hidden within its faint temperature variations would soon reveal how galaxies and cosmic structures first began to form. When scientists first measured the cosmic microwave background, one feature stood out immediately. The radiation looked almost perfectly uniform, no matter where astronomers pointed their instruments in the sky. The temperature of this faint microwave glow appeared nearly identical. In every direction, the radiation corresponded to a temperature of about 2.7 Kelvin. At first glance, that uniformity seemed almost too perfect, but cosmologists knew that if the universe truly formed galaxies, stars, and clusters of matter over billions of years, then the early universe could not have been completely smooth. There must have been tiny variations, regions where matter was just slightly denser than average, other areas where it was slightly less dense. Without those variations, gravity would have had nothing to work with. Matter would remain evenly distributed forever, and galaxies would never form. The challenge was that if these fluctuations existed, they had to be extremely small. If the early universe had been too uneven, gravity would have collapsed matter too quickly into enormous clumps. The universe might have ended up dominated by giant black holes rather than delicate galaxies and stars. But if it had been perfectly smooth, no structure would have formed at all. Cosmologists therefore expected the early universe to contain very subtle irregularities. The question was whether those irregularities could be detected. During the 1980s, scientists began designing increasingly sophisticated instruments to measure the cosmic microwave background with much higher precision. One of the most important missions dedicated to this task was the Cosmic Background Explorer satellite, often called COBE. The satellite was launched by the National Aeronautics and Space Administration in the late 1980s. Its goal was to study the cosmic microwave background above the distorting effects of Earth's atmosphere. COBE carried several instruments, including one specifically designed to measure temperature differences across the sky. What the satellite discovered in the early 1990s was extraordinary. The cosmic microwave background was not perfectly smooth after all. Instead, it contained incredibly tiny temperature variations. These variations were extremely subtle. The differences between the slightly warmer and slightly cooler regions were only about 1 part in 100,000. In terms of temperature, the fluctuations amounted to differences of roughly 1/10,000th of a degree Kelvin. Yet despite their small size, these variations carried enormous significance. They represented tiny differences in density present in the universe when it was only 380,000 years old. In slightly denser regions, gravity would pull matter inward more strongly. Over millions and then billions of years, those regions would accumulate more material. Eventually they would form galaxies, clusters of galaxies, and the vast cosmic structures we observe today. In other words, the faint temperature variations discovered by COBE were essentially the earliest visible seeds of cosmic structure. George Smoot, one of the scientists involved with the COBE mission, famously described the result by saying that observing the fluctuations was like seeing the face of God. The phrase was poetic rather than literal, but it captured the excitement of the discovery. For the first time, scientists were directly observing the initial conditions that would eventually lead to the formation of galaxies. COBE's measurements were groundbreaking, but they were only the beginning. Later missions would map the cosmic microwave background with far greater precision. One of these missions was the Wilkinson Microwave Anisotropy Probe, often called WMAP. Launched by the National Aeronautics and Space Administration in the early 2000s, WMAP measured the microwave background with dramatically improved resolution. Its observations produced a detailed map of temperature fluctuations across the entire sky. These maps revealed a rich pattern of slightly warmer and slightly cooler regions spread across the cosmic background radiation. Each of those subtle variations corresponded to differences in density present in the early universe. Scientists used the data from WMAP to determine key cosmological properties, including the age of the universe, the amount of ordinary matter present, and the overall geometry of space. The results strongly supported the picture of a universe that began in a hot and dense state, and evolved over billions of years. Even more detailed measurements arrived later, with a mission led by the European Space Agency. This spacecraft was called Planck. The Planck satellite was launched in the late 2000s and carried extremely sensitive instruments capable of measuring temperature variations in the cosmic microwave background with remarkable precision. Planck's observations produced the most detailed map of the early universe ever created. The patterns revealed in those maps were not random. They contained specific statistical properties predicted by theories of cosmic evolution. In particular, The distribution of fluctuations matched expectations based on the influence of gravity acting over billions of years. But the story of these tiny variations goes even deeper. Cosmologists believe that the density fluctuations observed in the cosmic microwave background may ultimately originate from processes that occurred during the earliest moments of the universe. According to modern cosmological theories, the universe experienced a brief period of extremely rapid expansion shortly after cosmic expansion began. This phase is known as cosmic inflation. During inflation, space itself expanded at an extraordinary rate, stretching microscopic quantum fluctuations to enormous cosmic scales. Quantum fluctuations arise naturally in quantum mechanics due to the inherent uncertainty in energy and position at very small scales. In ordinary circumstances, these fluctuations remain confined to extremely tiny distances. But during cosmic inflation, the expansion of space magnified those fluctuations dramatically. Tiny irregularities that originally existed at subatomic scales were stretched across regions of space many millions of light-years wide. When inflation ended, those amplified fluctuations became frozen into the structure of the universe. Over time, gravity amplified them further, gradually building the complex cosmic web of galaxies and clusters we observe today. In this way, the largest structures in the universe may ultimately trace their origins back to quantum fluctuations that occurred in the earliest fractions of a second after cosmic expansion began. It is a remarkable connection between the smallest scales of quantum physics and the largest scales of cosmology. The faint patterns visible in the cosmic microwave background therefore tell a profound story. They show that the universe began in a state that was extremely smooth, but not perfectly uniform. Within that near uniformity were tiny variations so small that they are measured in millionths of a degree. Yet those minute differences eventually guided the formation of galaxies, stars, and planetary systems, including the one that allowed life to emerge here on Earth. The vast structures of the cosmos were built from the quiet imprint of those early fluctuations, a delicate pattern written into ancient light nearly 14 billion years ago. Long before the first stars began shining, the universe had already begun shaping the simplest building blocks of matter. Those first moments after cosmic expansion began were unimaginably energetic. Temperatures were so extreme that matter existed as a dense mixture of fundamental particles moving at enormous speeds. Protons, neutrons, electrons, and photons collided constantly within a blazing cosmic plasma. Yet even within that intense environment, the laws of nuclear physics were quietly guiding the formation of the very first atomic nuclei. This process is known as Big Bang nucleosynthesis. The term nucleosynthesis simply refers to the creation of atomic nuclei. In everyday conditions, the nuclei of atoms remain stable and do not easily change their composition. But at extremely high temperatures and densities, nuclear reactions can occur rapidly, allowing particles to combine into new atomic structures. In the early universe, these reactions began only a few minutes after cosmic expansion started. To understand why that timing matters, it helps to remember that the universe was expanding and cooling at the same time. During the earliest fractions of a second, temperatures were far too high for stable nuclei to exist. Any attempt by protons and neutrons to combine would immediately be disrupted by the intense energy of surrounding radiation. But as the universe expanded, temperatures gradually fell. Once the temperature dropped to roughly 1 billion Kelvin, conditions became favourable for certain nuclear reactions to proceed. Protons and neutrons could begin binding together. The simplest nucleus that can form from these particles is the nucleus of deuterium, sometimes called heavy hydrogen. A deuterium nucleus contains one proton and one neutron bound together. Once deuterium nuclei formed, additional reactions could follow. Deuterium nuclei could combine with other protons and neutrons to form slightly heavier nuclei. Through a chain of nuclear reactions, some of this material assembled into helium nuclei. A helium nucleus contains 2 protons and 2 neutrons, making it significantly more stable than lighter combinations of particles. As these reactions continued, a small amount of lithium nuclei also formed, but the process did not produce heavier elements in large quantities. There were 2 important reasons for this. First, the early universe expanded and cooled very rapidly. The window of time during which nuclear reactions could occur lasted only a few minutes. Second, there are certain nuclear configurations that act as barriers to forming heavier elements. In particular, there are no stable nuclei with 5 or 8 nucleons. These gaps make it extremely difficult to build larger atomic nuclei through simple fusion reactions in the early universe. As a result, Big Bang nucleosynthesis produced only a limited set of elements. The vast majority of ordinary matter emerging from those early minutes consisted of hydrogen nuclei, which are simply single protons. A significant fraction formed helium nuclei, and only a trace amount formed lithium. In terms of overall proportions, the predictions were very specific. Calculations showed that roughly 3/4 of the ordinary matter in the universe should be hydrogen, while about 1/4 should be helium. Lithium should exist only in extremely small quantities. These predictions were developed by physicists studying nuclear reactions and cosmological expansion during the 1940s and 1950s. Researchers such as George Gamow, Ralph Alpher, and Robert Herman played important roles in linking nuclear physics with cosmology. Their work showed that the abundance of light elements in the universe could serve as a powerful test of the hot early universe model. If the Big Bang model was correct, the proportions of hydrogen, helium, and lithium observed throughout the universe should match the predictions of Big Bang nucleosynthesis. At the time these calculations were made, measuring such elemental abundances across the cosmos was extremely difficult. Astronomers did not yet have the observational tools needed to analyze distant gas clouds with great precision. But as telescopes improved and spectroscopic techniques advanced, scientists gradually began gathering the necessary data. One of the most useful methods involves studying primordial gas clouds. These clouds consist of relatively pristine material that has undergone very little chemical processing inside stars. Because they have not been significantly altered by stellar activity, they preserve the original chemical composition produced in the early universe. Astronomers can analyze the light from distant quasars that passes through these clouds on its way to Earth. When light travels through a cloud of gas, specific wavelengths are absorbed by different elements. By examining these absorption patterns, scientists can determine which elements are present and in what quantities. Observations of such gas clouds revealed something remarkable. The relative abundance of hydrogen and helium matched the predictions of Big Bang nucleosynthesis extremely well. Helium makes up about 1/4 of the ordinary matter in the universe, almost exactly what the theory predicted. Lithium is present in much smaller amounts, though its exact abundance remains an active area of research, because measurements sometimes show slight discrepancies with theoretical expectations. Even so, the overall agreement between prediction and observation is striking. The early universe appears to have produced precisely the mixture of light elements expected from a hot and dense beginning. This agreement represents a powerful connection between nuclear physics and cosmology. Nuclear physics describes how atomic nuclei form and interact under extreme conditions. Cosmology describes the evolution of the universe on the largest scales imaginable. In the case of Big Bang nucleosynthesis, these two fields intersect beautifully. By understanding nuclear reactions at the smallest scales, scientists can predict the chemical composition of the entire universe. And when astronomers observe that composition billions of years later, it matches those predictions remarkably well. Few scientific theories manage to connect such vastly different scales of nature so successfully. From the subatomic interactions between protons and neutrons to the chemical makeup of distant galaxies, the same physical laws apply. This harmony between theory and observation provides another strong piece of evidence supporting the idea that the universe once existed in a hot and dense state. The lightest elements we see throughout the cosmos were forged during the first few minutes of cosmic history. Everything heavier would come later, produced inside the fiery cores of stars. But the earliest chapter of chemical creation unfolded almost immediately after the universe began expanding, when nuclear reactions shaped the first atomic nuclei within the young and rapidly cooling cosmos. The early universe began remarkably smooth, but not perfectly smooth. Tiny variations in density were present almost from the beginning. Some regions contained slightly more matter than average, while others contained slightly less. The differences were incredibly small, measured in fractions of a degree within the cosmic microwave background. Yet those tiny irregularities would eventually determine the entire large-scale structure of the universe. The force responsible for this transformation is gravity. Gravity acts wherever mass exists, and it always pulls matter toward other matter. Even a slightly denser region of space exerts a stronger gravitational pull than its surroundings. Over time, this difference begins to matter. Imagine a gentle depression forming in a flat landscape after rainfall. Water slowly flows toward the lowest point, The deeper the depression becomes, the more water it attracts. Gravity operates in a similar way across the universe. Regions containing slightly more mass begin pulling additional matter toward them. As more matter gathers, the gravitational pull becomes stronger still. This feedback process gradually amplifies the tiny density variations that were present in the early universe. At first, the changes occur slowly. For millions of years after the universe became transparent, matter continued drifting through space in a fairly uniform distribution. But gravity was quietly working in the background. Gradually, matter began to collect into faint clumps. Those clumps grew denser over time, eventually forming the first gravitationally bound structures. Within these regions, gas collapsed under its own weight until temperatures and pressures rose high enough to ignite nuclear fusion. The first stars were born. Those early stars were very different from most stars seen today. Because the early universe contained almost no heavy elements, the first generation of stars formed from nearly pure hydrogen and helium. Many of them were likely extremely massive, perhaps tens or even hundreds of times more massive than the Sun. These stars burned brightly but briefly. Their intense radiation and powerful supernova explosions began enriching the surrounding gas with heavier elements such as carbon, oxygen, and iron. As time passed, gravity continued shaping matter into larger structures. Small collections of stars gathered into the earliest galaxies. Galaxies began clustering together. Over hundreds of millions and then billions of years, the universe developed a vast network of cosmic structures. But there was another ingredient involved in this process that scientists gradually came to recognize. That ingredient is dark matter. Dark matter is a form of matter that does not emit, absorb, or reflect light. It cannot be seen directly with telescopes, yet its gravitational influence is unmistakable. Astronomers first noticed evidence for dark matter while studying the motion of galaxies and galaxy clusters. In the 1930s, Swiss astronomer Fritz Zwicky examined the movement of galaxies inside the COBE cluster. He found that the galaxies were moving much faster than expected, based on the visible mass of the cluster. According to the laws of gravity, the cluster should have flown apart unless a large amount of unseen mass was present. Later observations revealed similar patterns within individual galaxies. Stars near the outer edges of galaxies were orbiting far too quickly to be held in place by the gravity of visible matter alone. These observations strongly suggested that a large amount of invisible mass surrounds galaxies. This invisible component became known as dark matter. Although scientists still do not know the exact nature of dark matter particles, they have determined that dark matter makes up a significant portion of the universe's total mass. In fact, ordinary matter, the atoms that form stars, planets, and people, accounts for only a small fraction of the universe's total matter content. Dark matter provides a kind of gravitational framework that helps shape cosmic structure. Because dark matter interacts very weakly with radiation, it began clumping under gravity earlier than ordinary matter. These early clumps of dark matter acted as gravitational wells that attracted gas made of hydrogen and helium. Ordinary matter then fell into these wells, eventually forming stars and galaxies. Without dark matter, galaxies would likely have taken much longer to form, and the large-scale structures we observe today might look very different. To understand how these processes unfold across billions of years, scientists use powerful computer simulations. One of the most influential projects in this field was developed by astrophysicist Volker Springel and his colleagues at the Max Planck Institute for Astrophysics in Germany. Springel led the development of large cosmological simulations such as the Millennium simulation. These simulations use the laws of gravity, hydrodynamics, and cosmology to track how matter evolves from the early universe to the present day. The simulations begin with the tiny density fluctuations observed in the cosmic microwave background. Then, using supercomputers, researchers allow gravity to act on those fluctuations over billions of simulated years. The results are astonishing. Matter gradually forms an intricate network of structures stretching across enormous distances. Dense clusters of galaxies appear at the intersections of long filaments of matter. Between these filaments lie vast regions of relatively empty space known as cosmic voids. Together, these structures form what astronomers call the cosmic web. The cosmic web spans the observable universe on scales of hundreds of millions of light-years. It resembles an enormous three-dimensional network with galaxies and clusters tracing delicate threads through space. When astronomers map the distribution of galaxies across the sky, They observe patterns that match the predictions of these simulations remarkably well. Large galaxy surveys, such as the Sloan Digital Sky Survey, have mapped the positions of millions of galaxies, revealing the same filamentary structures predicted by cosmological models. The agreement between observation and simulation is striking. It suggests that the tiny density variations seen in the cosmic microwave background truly were the seeds from which cosmic structure grew. Over billions of years, gravity amplified those subtle differences until they produced the vast network of galaxies, clusters, and filaments that fill the universe today. In this way, the largest structures in existence trace their origins back to minute fluctuations in the early universe. A faint imprint in ancient radiation eventually became the grand architecture of the cosmos. And when scientists compare the observed cosmic web with predictions derived from the Big Bang model, the two align remarkably well. The universe appears to have evolved exactly as those early density fluctuations and gravitational processes suggested it would. From the smallest variations in temperature to the largest structures spanning hundreds of millions of light years, the cosmos reveals a consistent story. A story written in gravity, matter, and the slow unfolding of cosmic time. Once scientists began mapping the distribution of galaxies and studying the faint radiation from the early universe, another intriguing question naturally followed. What is the overall shape of the universe itself? At first glance, this question might seem almost philosophical. After all, space appears to stretch outward in every direction for unimaginable distances. Yet modern cosmology treats this question as a precise scientific problem involving geometry and topology. Geometry describes how space is curved or flat on large scales. Topology describes how space might be connected to itself in ways that are not immediately obvious. Together, these ideas form the field known as cosmic topology, the study of the universe's global structure. To understand why this matters, it helps to recall one of the key insights from Albert Einstein's theory of general relativity. According to general relativity, mass and energy influence the curvature of space-time. Large amounts of matter can bend the geometry of space, shaping the paths that objects and light follow. This means that the universe itself can possess different geometric forms depending on its total matter and energy content. Cosmologists usually describe three main possibilities. The first possibility is a flat universe. In a flat universe, the geometry of space follows the familiar rules of Euclidean geometry. Parallel lines remain parallel, and the angles of a triangle add up to 180 degrees. If the universe is perfectly flat on large scales, then light travelling through space does not gradually converge or diverge due to curvature. The second possibility is a positively curved universe. In this scenario, space curves in a manner somewhat similar to the surface of a sphere. On a spherical surface, lines that begin parallel can eventually meet. A triangle drawn across such a surface would have angles that add up to more than 180 degrees. A positively curved universe could be finite in size, though it would not necessarily have an edge. Just as the surface of the Earth is finite but has no boundary where the surface suddenly stops, a curved universe could wrap around itself smoothly. The third possibility is a negatively curved universe. In this case, space curves in the opposite direction, somewhat like the shape of a saddle. Lines that begin parallel gradually diverge, and the angles of a triangle add up to less than 180 degrees. Each of these geometries leads to different predictions about how light travels across cosmic distances. Astronomers can therefore test the shape of the universe by carefully examining distant observations. One of the most powerful tools for this investigation comes from the cosmic microwave background. The tiny fluctuations in temperature across the microwave background form patterns that correspond to specific physical scales in the early universe. When scientists measure how large those patterns appear in the sky, they can infer how space has curved during the billions of years that light has travelled toward us. If space was strongly curved, the apparent sizes of these features would differ from the predictions of a flat geometry. Observations from missions such as the Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite have measured these patterns with extraordinary precision. The results indicate that the universe is very close to geometrically flat on the largest observable scales. That does not necessarily mean the universe is infinite, but it does suggest that if curvature exists, it is extremely subtle. Beyond simple curvature, cosmologists also explore more complex possibilities involving topology. Topology describes how space might be connected to itself. A useful way to visualize this idea is to imagine the surface of a video game where a character who walks off the right side of the screen immediately reappears on the left side. Although the screen appears flat, the underlying topology connects its edges. Similarly, the universe might have a topology that causes space to wrap around itself. In such a universe, traveling far enough in one direction might eventually bring you back to your starting point. Some cosmologists have explored specific models in which the universe possesses unusual topological shapes. One example was proposed by French astrophysicist Jean-Pierre Luminet and his collaborators. Luminet studied the possibility that the universe could have a shape resembling a dodecahedron. A dodecahedron is a geometric solid with 12 pentagonal faces. In Luminet's model, opposite faces of this shape would be connected in such a way that space wraps around itself. This configuration would produce distinctive repeating patterns in the cosmic microwave background. Astronomers have searched for such patterns as potential evidence for a multiply-connected universe. So far, observations have not revealed clear confirmation of that specific model, but the search itself demonstrates how subtle clues in ancient radiation can reveal the geometry of the cosmos. The shape of the universe is closely tied to the dynamics of cosmic expansion. The overall density of matter and energy determines how strongly space curves and how expansion evolves over time. If the density of the universe were high enough, gravity might eventually slow the expansion and cause the universe to collapse. If the density were lower, expansion could continue forever. Modern measurements suggest that the universe contains a mixture of ordinary matter, and dark energy. Together, these components determine the geometry and long-term behavior of cosmic expansion. Observations indicate that the total energy density of the universe is very close to the critical value required for a flat geometry. This delicate balance may not be a coincidence. Some theories propose that an early phase of rapid expansion known as cosmic inflation could naturally drive the universe toward flatness. Regardless of the underlying cause, the study of cosmic geometry has become one of the most precise areas of modern cosmology. By analyzing faint patterns in ancient radiation and measuring the distribution of galaxies across enormous distances, scientists can investigate the shape of space itself. It is a remarkable achievement. Humanity, living on a small planet orbiting an ordinary star, has learned how to measure the curvature of the entire universe. And the answer appears to be that space, at least across the observable cosmos, is remarkably close to flat. Yet the deeper topological structure of the universe remains one of the great unanswered questions of cosmology. Somewhere within the faint glow of ancient light and the distribution of distant galaxies, the true geometry of the cosmos continues to reveal itself slowly and patiently to those who study the sky. As cosmologists studied the early universe in greater detail, they encountered several puzzles that were surprisingly difficult to explain. The Big Bang model already described a universe that began hot, dense, and expanding. It explained the cosmic microwave background, the abundance of light elements, and the large-scale structure of galaxies. Yet some observations hinted that the earliest moments of cosmic history might have been even stranger than initially imagined. One of the most intriguing puzzles became known as the horizon problem. To understand this issue, consider the remarkable uniformity of the cosmic microwave background. When astronomers measure the temperature of this radiation in different directions across the sky, they find that it is almost identical everywhere. The variations are incredibly small, only about 1 part in 100,000. This means that regions of the universe separated by vast distances appear to have almost exactly the same temperature. At first glance, this might not seem surprising, but when scientists calculated how far light could have travelled in the early universe, they discovered something puzzling. Regions on opposite sides of the sky are separated by such enormous distances that they could never have exchanged information in the time available since the universe began expanding. In other words, those regions appear to have never been in contact with one another, and yet their temperatures are nearly identical. This raises a natural question. How did distant parts of the universe manage to reach the same temperature if they were never able to interact? It would be a bit like finding 2 cups of coffee placed in different rooms of a house, both cooling to exactly the same temperature, even though the rooms have never shared any air. The puzzle suggested that something unusual must have happened very early in cosmic history. In the early 1980s, a physicist named Alan Guth proposed a remarkable solution. Guth suggested that the universe may have undergone a brief period of extremely rapid expansion, shortly after cosmic expansion began. This idea became known as cosmic inflation. According to the inflation theory, the universe expanded exponentially during a tiny fraction of a second after its earliest moments. The expansion was not merely fast, it was extraordinarily fast. During inflation, the size of the universe may have increased by an enormous factor in an incredibly short time. To give a sense of scale, physicists estimate that the universe could have expanded by at least a factor of 10 to the power of 26 during this brief interval. That number represents a 1 followed by 26 zeros. To visualize such growth, imagine an object the size of a subatomic particle expanding to something roughly the size of a galaxy, and all of that happening in far less than a second. This rapid expansion offers an elegant solution to the horizon problem. Before inflation occurred, the universe would have been much smaller. Regions that now lie far apart would once have been close enough to interact. They could have exchanged energy and reached the same temperature. Then inflation dramatically stretched space, separating those regions across enormous distances. As a result, the universe today appears uniform across regions that no longer share any direct connection. Inflation also helps explain another cosmological puzzle known as the flatness problem. Observations show that the geometry of the universe is extremely close to flat. But in the absence of inflation, maintaining such near-perfect flatness over billions of years would require extremely precise initial conditions. Inflation naturally drives the geometry of space toward flatness as it stretches the fabric of the universe. In this way, inflation provides a mechanism that explains several otherwise puzzling features of the cosmos. But perhaps the most fascinating aspect of inflation involves quantum physics. At extremely small scales, quantum mechanics tells us that energy and fields cannot remain perfectly smooth. Instead, tiny fluctuations constantly appear and disappear due to the inherent uncertainty present in quantum systems. These quantum fluctuations normally occur on incredibly small scales, far smaller than atoms. However, during the inflationary expansion, these fluctuations would have been stretched dramatically. Minute variations in energy present within the quantum fields of the early universe would expand along with space itself. As inflation continued, those fluctuations would grow from microscopic scales to astronomical sizes. When inflation eventually ended, the stretched fluctuations would remain embedded in the density of matter and energy throughout the universe. Over time, gravity would amplify these variations further. Regions with slightly higher density would attract additional matter, eventually forming galaxies and clusters of galaxies. In this way, quantum fluctuations from the earliest fractions of a second may have become the seeds of cosmic structure. The idea that the largest structures in the universe originated from quantum effects at subatomic scales is one of the most remarkable connections in modern physics. Inflation theory did not remain static after Guth's initial proposal. Other physicists soon began exploring variations and extensions of the idea. One important contributor was Andrei Linde, a Russian physicist who later worked in the United States. Linde developed models known as chaotic inflation. In these models, inflation does not occur only once in a single region of space. Instead, different regions of spacetime can undergo inflation independently. Some regions inflate rapidly, while others stop inflating earlier. This concept leads to the possibility that inflation may produce many separate regions of space with different properties. In some interpretations, chaotic inflation naturally leads to the idea of a multiverse, where many distinct universes could exist within a much larger cosmic framework. Another important contributor to inflationary cosmology was Paul Steinhardt. Steinhardt worked on early models that refined the mathematics of inflation and helped explore how inflation might begin and end within realistic physical theories. Although Steinhardt later developed alternative cosmological ideas, his early contributions played an important role in shaping inflationary theory. Today, inflation remains one of the most influential ideas in cosmology. Observations of the cosmic microwave background show patterns of temperature fluctuations that match many predictions made by inflationary models. These patterns suggest that the tiny density variations observed in the early universe could indeed have originated from quantum fluctuations stretched by rapid expansion. Scientists continue searching for additional evidence that could confirm or refine inflationary theory. Some experiments attempt to detect subtle patterns in the polarization of the cosmic microwave background that might reveal the presence of gravitational waves produced during inflation. If detected, such signals would offer direct clues about the earliest moments of cosmic history. The idea of inflation invites us to imagine a universe that experienced an almost unimaginable transformation during its earliest fraction of a second. Space itself expanded at extraordinary speed, smoothing out irregularities while simultaneously stretching tiny quantum fluctuations into cosmic seeds. From those seeds would grow the galaxies, stars, and planets that fill the universe today, and perhaps, eventually, the curious minds capable of asking how it all began. When scientists follow the expansion of the universe backward in time, the equations of classical cosmology lead to an extraordinary conclusion. The universe appears to approach a state of extreme density and temperature. If this trend continues all the way to its limit, the mathematics predicts what physicists call a singularity. A singularity is a point where physical quantities such as density, temperature, and curvature become infinitely large. At such a point, the known laws of physics can no longer describe what is happening. This prediction emerges directly from the equations of general relativity developed by Albert Einstein. Yet physicists understand that general relativity is not the complete description of nature. General relativity works exceptionally well when describing gravity on large scales, such as the motion of planets, the behavior of stars, and the expansion of the universe. But another theory governs the behavior of matter and energy at extremely small scales. That theory is quantum mechanics. Quantum mechanics describes the strange and fascinating behavior of particles at microscopic distances. It explains phenomena such as atomic structure, chemical reactions, and the behavior of subatomic particles. In everyday circumstances, general relativity and quantum mechanics operate in separate domains. Gravity dominates the behavior of massive objects across large distances. Quantum mechanics governs the tiny world of atoms and particles. However, the earliest moments of cosmic history involve both extreme density and extremely small scales. In such conditions, gravity and quantum physics must both play essential roles. This realization has led physicists to search for a theory that unifies general relativity with quantum mechanics. Such a theory is often referred to as quantum gravity. Although a complete theory of quantum gravity remains one of the great unsolved challenges of physics, scientists have developed several promising approaches. These approaches attempt to describe what may have happened during the earliest moments of cosmic history, when the universe was far smaller and denser than it is today. One influential idea emerged from the work of James Hartle and Stephen Hawking. Their proposal is often called the no-boundary model of the universe. Hartle and Hawking suggested that the beginning of the universe might not involve a singular starting point in time. Instead, they proposed that time itself may behave differently at extremely small scales. To illustrate their idea, they introduced a concept known as imaginary time. Although the term might sound mysterious, imaginary time is simply a mathematical transformation used in certain areas of physics. By treating time as a dimension similar to space, the equations describing the early universe become smoother and more well-behaved. In this framework, the universe does not begin at a sharp boundary. Instead, the geometry of space-time becomes rounded and finite, somewhat like the surface of the Earth. On Earth, there is no special point that marks the beginning of the planet's surface. If you travel northward, you eventually reach the North Pole, but that location is not an edge or boundary. It is simply a point where the direction of travel changes. Hartley and Hawking suggested that the beginning of cosmic time might resemble this situation. The universe could be finite yet without a true boundary in time. In such a model, asking what happened before the beginning of the universe might be similar to asking what lies north of the North Pole. The question itself may not have a meaningful answer. Another fascinating approach was proposed by cosmologist Alexander Vilenkin. Vilenkin explored the possibility that the universe could emerge through a process related to quantum tunneling. Quantum tunneling is a well-known phenomenon in quantum mechanics. It allows particles to pass through barriers that would be impossible according to classical physics. For example, electrons inside atoms can sometimes move through energy barriers that they do not have enough energy to cross in the classical sense. This process occurs because quantum particles are described by wave functions that spread across space, giving them a probability of appearing on the other side of a barrier. Vilenkin applied this concept to the entire universe. In his model, the universe could originate through a quantum tunneling event from a state with no classical spacetime. Rather than beginning with an infinite density singularity, the universe could appear spontaneously as a small quantum fluctuation that then expands into the cosmos we observe today. The idea might sound almost philosophical, yet it arises from serious attempts to apply quantum principles to cosmology. Another major line of research comes from the study of loop quantum gravity. This approach attempts to describe space-time itself as having a discrete structure at extremely small scales. One of the leading researchers in this field is Abhay Ashtekar. Ashtekar and his collaborators have developed mathematical frameworks suggesting that space-time may be composed of tiny loops or units of quantum geometry. Within loop quantum gravity, the classical singularity predicted by general relativity may never actually form. Instead of collapsing into infinite density, the universe might reach a minimum size and then rebound. This possibility leads to the concept of a cosmic bounce. In a bouncing universe model, the expansion we observe today could have been preceded by an earlier phase in which the universe was contracting. When the density became extremely high, quantum gravitational effects would prevent further collapse and cause the universe to begin expanding again. Such models are still under active investigation, but they demonstrate how quantum gravity could fundamentally alter our understanding of the earliest moments of cosmic history. All of these ideas fall within the broader field known as quantum cosmology. Quantum cosmology seeks to describe the origin and evolution of the universe using principles derived from quantum physics. Rather than treating the universe as a purely classical system, governed only by general relativity, quantum cosmology explores how quantum processes may influence the behavior of space-time itself. This field remains highly theoretical, but it offers valuable insights into questions that classical cosmology cannot answer. The Big Bang model successfully describes the evolution of the universe from a hot and dense early state onward. However, it does not fully explain what happened during the very first fraction of a second. Near the beginning of cosmic expansion, densities and energies become so extreme that classical physics reaches its limits. Quantum cosmology attempts to extend our understanding into that frontier. Some theories suggest the universe may have emerged from quantum fluctuations. Others propose that time itself may not have a traditional beginning. Still others explore the possibility that cosmic expansion followed a previous phase of contraction. Although many of these ideas remain speculative, they represent a natural continuation of the scientific effort to understand the universe. By combining the insights of quantum mechanics with the geometry of general relativity, physicists hope to illuminate the earliest moments of cosmic history. Moments that occurred long before the first atoms formed, long before the first light travelled freely through space, and long before the structures of galaxies and stars began to take shape. In that mysterious era, the universe may have behaved in ways that challenge our everyday intuition, and yet within those earliest moments may lie the deepest clues to how the cosmos itself came into existence. Even though the Big Bang model explains many observations with remarkable success, cosmologists have continued exploring alternative ideas about how the universe might have begun. Some of these ideas do not reject cosmic expansion or the hot early universe. Instead, they attempt to reinterpret what happened before that early state, or whether the Big Bang was truly the absolute beginning of everything. In classical cosmology, tracing the expansion of the universe backward leads to a singularity, a point of infinite density where the known laws of physics break down. Many physicists suspect that this singularity represents a limitation of the mathematical model rather than a literal event that occurred in nature. Because of that possibility, researchers have proposed cosmological scenarios in which the universe avoids a singular beginning altogether. One of the most intriguing proposals comes from a theory known as the ekpyrotic universe. This idea was developed by physicists Paul Steinhardt and Neil Turok in the early 2000s. Their model draws inspiration from concepts in string theory, which attempts to describe fundamental particles as tiny vibrating strings existing within higher dimensional spaces. In the ekpyrotic model, our universe may exist on a three-dimensional surface, often called a brane, embedded within a higher dimensional space. Another brane may exist nearby within that higher dimensional structure. According to the theory, the Big Bang was not the creation of the universe from nothing. Instead, it was the result of a collision between these branes. When the two branes approached each other and eventually collided, enormous amounts of energy were released. That energy produced the hot and dense conditions associated with the beginning of cosmic expansion. In this scenario, the Big Bang represents a transition rather than an absolute beginning. The universe could have existed in some form before the collision occurred, Some versions of the ekpyrotic model even suggest that such collisions may happen repeatedly over extremely long periods of time. Each collision could trigger a new phase of cosmic expansion, leading to a universe that cycles through repeated stages of contraction and rebirth. Another alternative approach emerges from loop quantum cosmology, which is closely related to the theory of loop quantum gravity. As mentioned earlier, loop quantum gravity attempts to describe space-time as having a discrete quantum structure, rather than being perfectly smooth. One of the physicists who helped develop cosmological models based on this idea is Martin Boijewald. Boijewald studied how quantum gravitational effects might alter the behavior of space-time when the universe becomes extremely dense. In classical general relativity, gravity always pulls matter inward. When matter becomes sufficiently dense, the equations predict that collapse continues indefinitely, producing a singularity. However, quantum effects can change this picture. According to loop quantum cosmology, space-time at extremely small scales behaves more like a quantum system with built-in limits. When the density of the universe becomes extremely high, quantum gravitational effects can produce a repulsive force. This repulsion prevents the formation of an infinite singularity. Instead of collapsing endlessly, the universe reaches a minimum size and then rebounds outward. This rebound is often called a cosmic bounce. In a bouncing cosmology, the expanding universe we observe today might have been preceded by an earlier contracting phase. The Big Bang would then represent the moment when contraction transitioned into expansion. This idea has an appealing symmetry. Rather than beginning with a singular event, the universe may pass through cycles of contraction and expansion, governed by the laws of quantum gravity. Another imaginative proposal comes from the renowned mathematical physicist Roger Penrose. Penrose developed a theory called conformal cyclic cosmology. The central concept of this theory is that the universe may pass through a sequence of cosmic eras known as aeons. According to Penrose, the extremely distant future of one universe could become mathematically equivalent to the beginning of the next. To understand this idea, consider what happens to the universe over enormous timescales. If cosmic expansion continues indefinitely, galaxies will drift farther apart, stars will eventually burn out, and matter may gradually decay into radiation and elementary particles. Over trillions of years, the universe could become extremely cold and empty. In such a scenario, Penrose suggests that the distinction between extremely large scales and extremely small scales may begin to lose meaning. When all matter has effectively vanished and only radiation remains, the universe may become conformally equivalent to a new beginning. In other words, the remote future of one cosmic era could smoothly transform into the birth of another. Each cycle would represent a new aeon, with its own Big Bang-like beginning. Penrose and his collaborators have even searched for possible observational signatures of previous aeons in the cosmic microwave background. The evidence remains controversial, but the theory demonstrates how imaginative cosmological models can arise from deep mathematical ideas. Despite their differences, all of these alternative cosmologies share a common goal. They attempt to describe the earliest phases of the universe without relying on a singular beginning where the laws of physics completely break down. Instead of a universe emerging from an infinitely dense point, these models explore possibilities such as collisions, quantum bounces, or repeating cosmic cycles. However, any successful cosmological theory must still explain the observations that the Big Bang model describes so well. The cosmic microwave background, the abundance of light elements, and the large-scale structure of galaxies all provide powerful constraints on any proposed model. Alternative cosmologies must reproduce these features with the same accuracy as the standard cosmological framework. For this reason, most researchers treat such models as ongoing areas of investigation, rather than established replacements for the Big Bang model. They represent creative attempts to explore what might lie beyond the limits of current understanding. And they remind us that cosmology remains a living science. Even when a theory explains many observations, scientists continue asking deeper questions. Questions about the true origin of cosmic expansion. Questions about whether the universe began once, or perhaps many times. And questions about whether the story of the cosmos might be far longer and more intricate than we currently imagine. As cosmologists explored the implications of cosmic inflation, some researchers began noticing that the mathematics suggested something even more surprising than a rapidly expanding early universe. Under certain conditions, inflation might never completely stop. Instead of occurring once and ending everywhere at the same time, inflation could continue indefinitely in different regions of space. This idea is known as eternal inflation. In eternal inflation models, the universe does not expand uniformly everywhere in the same way. Some regions stop inflating and form expanding universes like the one we inhabit. Other regions continue inflating, creating new regions of space that can themselves give rise to additional expanding universes. Each region where inflation ends becomes a kind of bubble universe. Inside such a bubble, space expands more gradually, allowing matter, radiation, galaxies, and stars to form. Meanwhile, outside that bubble, inflation continues stretching space and generating new regions where the process may repeat again. The result is a vast and potentially endless cosmic structure, sometimes described as a multiverse. The multiverse concept suggests that our observable universe may be only one small region within a far larger collection of universes. Each of these regions could possess its own properties, its own history, and possibly even its own physical laws. One physicist who has explored these ideas extensively is Max Tegmark of the Massachusetts Institute of Technology. Tegmark proposed a classification system that organizes different multiverse concepts into several levels. In what he calls Level 1, the multiverse arises simply because the observable universe has a limited size. Space beyond the region we can see may continue indefinitely, containing distant regions where matter is arranged differently but governed by the same physical laws. In Level 2, the multiverse emerges from eternal inflation. Different bubble universes may form with slightly different physical conditions, perhaps involving variations in fundamental constants, such as particle masses or interaction strengths. Level 3 relates to the many worlds interpretation of quantum mechanics, which proposes that every quantum event may create multiple branching outcomes. Level 4, Tegmark's most speculative category, suggests that all mathematically possible universes might exist as physical realities. Not all physicists accept this classification, but it illustrates how the multiverse concept can take several different forms depending on the theoretical framework involved. Another influential contributor to multiverse ideas is Leonard Susskind, a theoretical physicist known for his work in string theory. String theory attempts to describe fundamental particles not as point-like objects, but as tiny vibrating strings existing in higher dimensional spaces. One of the surprising features of string theory is the enormous number of possible solutions it allows. Each solution corresponds to a different configuration of physical laws, particle properties, and cosmic parameters. This enormous collection of possibilities is often called the string theory landscape. Estimates suggest that the number of possible configurations in this landscape may be extraordinarily large, sometimes described as 10 to the power of 500. That number represents 1 followed by 500 zeros. Within the context of eternal inflation, different bubble universes could settle into different locations within this landscape. Each bubble might possess slightly different physical constants. For example, the strength of gravity, the masses of elementary particles, or the energy associated with empty space might vary from one universe to another. This possibility raises a fascinating question. Why does our universe have the particular properties we observe? Why does gravity have the strength it does? Why do particles have the masses they possess? Some scientists have suggested that the multiverse may offer a possible explanation. If many universes exist with different physical properties, then observers will naturally find themselves in regions where the conditions allow complex structures to form. A universe with drastically different constants might expand too rapidly for galaxies to form, or collapse too quickly for stars to exist. In such universes, observers would never arise to ask questions about cosmic origins. Our universe may simply be one of the regions where the conditions happen to permit the formation of stars, planets, chemistry, and life. This idea is sometimes linked to a concept called the anthropic principle, which suggests that the properties of the universe we observe are influenced by the requirement that observers exist to measure them. While the multiverse concept is intellectually fascinating, it also raises important scientific questions. One of the central challenges involves testability. Science traditionally relies on observations and experiments to confirm or reject theoretical ideas. If other universes exist far beyond the boundaries of our observable universe, detecting them directly may be extremely difficult or perhaps impossible. Some researchers have suggested possible indirect clues. For example, If bubble universes occasionally collide during the early stages of cosmic inflation, such collisions might leave subtle imprints in the cosmic microwave background. Scientists have searched for such signals, although no conclusive evidence has yet been found. Other researchers argue that the multiverse idea emerges naturally from established physical theories and therefore deserves serious consideration even if direct observation remains challenging. Still others remain skeptical, suggesting that scientific explanation should focus primarily on phenomena that can be tested through observation. The debate continues within the cosmology community. Regardless of where one stands in that debate, the multiverse concept highlights the extraordinary scope of modern cosmological thinking. Just a century ago, astronomers were still debating whether the Milky Way represented the entire universe. Today, scientists seriously discuss the possibility that our universe may be one region within a much larger cosmic structure containing countless others. Whether or not the multiverse ultimately proves correct, the idea demonstrates how exploring the earliest moments of cosmic history can lead to profound questions about the nature of reality itself. Questions about the size of the cosmos, questions about the laws of physics, and questions about whether our universe might be only one small part of a far grander cosmic landscape. After more than a century of observation, calculation, and debate, cosmologists have assembled a remarkably consistent picture of how the universe has evolved. The idea that the universe began in a hot and dense state, followed by billions of years of expansion and cooling, is supported by several independent lines of evidence. What makes this picture so compelling is not just that it explains one observation, it explains many observations at once. Each piece of evidence arises from a different branch of science. Each involves different instruments, different methods, and often entirely different research communities. Yet when these pieces are assembled together, they tell a coherent and remarkably consistent story. One of the first clues came from the discovery of cosmic expansion. When Edwin Hubble studied distant galaxies at Mount Wilson Observatory during the 1920s, he found that their light was shifted toward longer wavelengths. This redshift indicated that galaxies are moving away from us. More importantly, the farther away a galaxy is, the faster it appears to recede. This relationship became known as Hubble's law, and it remains one of the most fundamental observations in cosmology. The simplest explanation for this pattern is that space itself is expanding. When the fabric of space stretches, galaxies become separated by increasing distances. Observers in any galaxy would see the same pattern, with all distant galaxies appearing to move away. This discovery suggested that the universe was once smaller in the past. If space is expanding today, then earlier in cosmic history it must have been denser and hotter. A second line of evidence arrived with the discovery of the cosmic microwave background. This faint radiation fills the entire sky and corresponds to a temperature of about 2.7 Kelvin. The radiation represents ancient light, released when the universe became transparent roughly 380,000 years after cosmic expansion began. Measurements of the microwave background have revealed that it possesses an almost perfect blackbody spectrum, exactly what physicists expect from radiation that once existed in thermal equilibrium within a hot and dense environment. Satellites launched by the National Aeronautics and Space Administration, including the Cosmic Background Explorer and the Wilkinson Microwave Anisotropy Probe, have mapped this radiation in extraordinary detail. Later, the European Space Agency launched the Planck satellite, which produced the most precise measurements of the cosmic microwave background to date. The temperature fluctuations observed in this radiation match predictions from theoretical models of the early universe with remarkable accuracy. A third line of evidence comes from the chemical composition of the cosmos. As described earlier, the first few minutes after cosmic expansion began provided the conditions necessary for nuclear reactions to occur. These reactions produce specific proportions of hydrogen, helium, and small amounts of lithium. This process, known as Big Bang nucleosynthesis, generated very precise predictions for the abundance of these light elements. Astronomers studying ancient gas clouds and distant galaxies have measured these abundances using spectroscopic observations. The results align closely with theoretical predictions. Approximately 3/4 of ordinary matter in the universe is hydrogen, while about 1/4 is helium. These proportions match what physicists calculate for a universe that began hot and dense and cooled rapidly during its earliest minutes. A fourth line of evidence arises from the large-scale structure of the universe. astronomical surveys mapping the positions of millions of galaxies reveal an intricate network known as the cosmic web. Galaxies cluster along vast filaments stretching hundreds of millions of light years, while enormous regions of relatively empty space form cosmic voids. Computer simulations based on the physics of gravitational growth reproduce these patterns when they begin with the tiny density fluctuations observed in the cosmic microwave background. Researchers such as Volker Springel and his collaborators have developed detailed cosmological simulations showing how gravity amplifies those small fluctuations into the complex structures we observe today. The agreement between simulation and observation is striking. Together, these independent lines of evidence converge on the same conclusion. The universe appears to have evolved from an early state that was extremely hot, extremely dense, and nearly uniform. Over billions of years, cosmic expansion allowed matter to cool, form atoms, gather into stars and galaxies, and eventually produce the vast structures we observe across the cosmos. This convergence is one of the hallmarks of strong scientific theories. The Big Bang model does not rely on a single observation or experiment. Instead, it integrates information from astrophysics, particle physics, nuclear physics, and observational astronomy. Each field contributes its own measurements and theoretical insights. When combined, they form a coherent narrative describing the history of the universe. Organizations around the world have played important roles in building this understanding. Space missions conducted by the National Aeronautics and Space Administration have measured the cosmic microwave background with remarkable precision. The European Space Agency has launched satellites such as Planck that refine those measurements even further. Ground-based observatories and galaxy surveys have mapped the distribution of matter across enormous regions of space. Together, these efforts represent decades of international collaboration involving thousands of scientists, engineers, and researchers. Despite its success, the Big Bang model is not considered the final word on cosmology. Science is not built on absolute certainty. Every scientific model remains open to revision as new evidence appears. Researchers continue searching for deeper insights into the earliest moments of cosmic history. Questions remain about the nature of dark matter and dark energy, the physics of cosmic inflation, and the possible role of quantum gravity near the beginning of time. Future observations may refine or extend the current model. New experiments may reveal unexpected phenomena that require adjustments to existing theories. But the central idea that the universe expanded from a hot and dense early state remains one of the most robust conclusions in modern science. What began as a tentative interpretation of distant galaxy motions has grown into a comprehensive framework describing nearly 14 billion years of cosmic evolution. The story is far from complete. Yet the evidence collected so far points consistently toward a universe that has been changing, cooling, and unfolding across vast stretches of time. And perhaps most remarkable of all is the fact that human beings, living on a small planet orbiting a fairly ordinary star, have managed to reconstruct this story using nothing more than careful observation, mathematics, and curiosity. The light from distant galaxies, the faint glow of ancient radiation, and the distribution of matter across the cosmos have together revealed a history written across the fabric of space itself. A history that stretches from the earliest moments of the universe all the way to the present day. And in understanding that history, we gain a deeper appreciation not only of the universe, but also of our place within it.